Okay, so welcome to the last talk of the day. Welcome to the last talk of the day. The speaker is Professor Kartik Prasanna from the University of Michigan, and he will speak on modular forms of weight 1, Motivic cohomology, and the Jacquet-Langlands correspondence.
Okay, yeah, so thanks, Iki, and thanks for the invitation to speak at this event. I'm sorry I can't be there in person. So today, what I'd like to tell you about is a story about algebraic cycles in some sense and their relation to Langlands functoriality. So let me just get going. All right, so the basic problem that I've been interested in some time is of the following sort. Suppose you have an automorphic form. Then to this, you can often associate some kind of geometric object. For example, so the kind of geometric objects I have in mind are, for example, Galois representations, or periods. So periods of automorphic forms are kind of geometric objects that are attached to them. And more generally, you could think about motives attached to automorphic forms. But so that's one sort of theme, which is if you start with an automorphic form, you can have such a geometric object. But then the question that I'm mainly interested in is the following. If you have two groups, say G1 and G2, and two automorphic forms, which I'll call pi1 and pi2, that are related in some way, usually by functoriality, then the question is, so you have, say, pi1, and you have some associated geometric objects to pi1, and likewise you have pi2, and these are related by functoriality. And the question is, how are these geometric objects related to each other? So this is a question that I've been interested in for a while, and I'm going to say a little bit about, give some background, and then say a little bit about some recent progress in this. In some sense, you can think about this as kind of geometric realizations of functoriality. Okay, so this is all very general and vague. So let me start by giving some examples. And I'll start with the simplistic case, this really simplest example, which is the case of modular forms for GL2 over Q. So just classical modular forms. So let's say I have F, a modular form of weight K, on gamma 1n. And we'll assume F is a new form, for example, just to be. And I'll also assume, for simplicity, that the Fourier coefficients of F live in Q. This is not important, but it's nice to have this for simplicity. Okay, so let's just recall what are the kind of geometric objects attached to such an F. And it turns out that when you think about attaching geometric objects to F, there's some kind of trichotomy. So there's the, depending on the weight. So there's this sort of simplest case, which is the case k equals 2. And then there's the case when k is bigger than 2. And finally, there's the case k equals 1, which is very special in some sense. So the case k equals 2 is really the simplest. Let's start with this case and just recall what we can say. So first, how does one construct the Galois representation? Well, you take the modular curve x equals x1 of n. And then you take the, there are two ways to do this. You can take the Jacobian, and then the Tate module of the Jacobian, or you can take H1 of X. So this is et al. Cohomology, dual coefficients. And so let me just introduce some notation. So I'll write pi for the automorphic representation attached to F. So here we would then take the pi isotopic component. So the meaning of this is we take the part of H1 on which the Hecke algebra acts by the same Hecke eigenvalues as it acts on pi. And this is a two-dimensional representation of the Galois group of Q. Okay, and equivalently, you could get this by taking the Tate module of the Jacobian. And then taking the dual. That's an equivalent way of saying the same thing. All right, so that's the Galois representation. And then you can think about Hodge structures. For example, periods or periods. And well, then you just think about X as a complex curve. And take H1 with Q coefficients. And this gives us a rational Hodge structure. That in some sense encodes at least some of the periods of F. Okay. So this guy breaks up as H1, 0, this H0, 1. So the way to think about this Hodge structure is this is a rational vector space such that its complexification has this added structure over here. It has a Hodge filtration and so on. But in this case, one gets actually something more. One gets a motive. In fact, a Chow motive. And you can realize this Chow motive in the H1 of this curve. H1 of either H1 of the curve or H1 of the Jacobian is the same thing. Okay, so that's what happens in the case k equals 2. The case k greater than 2 is a bit more difficult because you can't quite do this construction. You can't just work with the modular curve, but you can still construct the Galois representation as follows. So this is done by Deline. So this was due to Shimura. So the case k bigger than 2, there are two ways to construct this Galois representation. One is you can take the so-called Kuga-Sato variety. So this is something that's fibered over X. And the way this is constructed is you take the universal elliptic curve over Y, which is Y is Y1 of n. And then you have to take a product of this. This is the k minus 2 product over Y1 of n. And then W is constructed as some sort of compactification. And this has been constructed by Deline. And now you can either look at HK minus 1 of W. This acquires sort of a Galois action. And or equivalently, another way to do this is you can think of H1 of the curve with coefficients in some local system, which I'll call LK. And again, you want to take the pi isotopic component. So these have Hecke actions, and then you take the pi isotopic component. So this is how the Galois representation is constructed. And of course, the Hodge structure can likewise be constructed simply by taking cohomology with C coefficients, for example. Okay, and finally, there's the case. Okay, so this case is a bit. The reason I said that k bigger than 2 is a bit harder is in this case, again, constructing a motive is a bit trickier. And there is a Grothendieck motive, which has been constructed by, so there's a Grothendieck motive constructed by Shaw. So already there's some difference between the case k equals 2 and k bigger than 2. And this motive can only be constructed as a growth, at least at this point, as a Grothendieck motive and not as a Chow motive. And there's some difference between these two. And finally, there's the case k equals 1. And this case is very special because the Galois representation. So the main reason this case is special is this is not cohomological. You can't find weight 1 forms in the cohomology of a Shimura variety. So constructing the Galois representation is trickier, but this has been done by Deline and Serre. And the idea is to use congruences. So you use the case k bigger than equals 2 to construct the Galois representations in the case k equals 1. So that's fine. But then you can ask, well, what about other things like the Hodge structure or the motive? So there is an Artin motive. You get in this way. But how about the periods? And so at the end of the talk, I will come and I'll sort of spend more time talking about the weight 1 case. But the basic point is that even though these are not cohomological, they do occur in coherent cohomology. So in fact, the Galois representations in every case is sort of 2-dimensional. And here, likewise, you have a 2-dimensional piece. But here, in the case when k is bigger than equals 2, the cohomology is entirely concentrated in H1 of so H1 here, or H1 or HK minus 1, depending on whether you take a local system or the Kuga-Saro variety. But here, something interesting happens. The cohomology is actually split across 2 cohomological dimensions. So and this is and each one of these has rank 1. So something interesting happens over here in the weight 1 case, and this is what I'll get to towards the end of the talk. Okay, so let me just say now the second question, or rather the main question. So recall the main question that I'm interested in is this question: if I have 2 groups G1 and G2, and I have 2 forms that are related in some way by functoriality, then how are these geometric objects related to each other? So again, this is simplest to understand in the case when k is equal to 2. And so here, the form of functoriality is what is called Jacquet-Langlands. And the way this comes about is you can start with B, a quaternion algebra over Q. And let's say it's indefinite. And Jacquet-Langlands give you very precise criteria for pi to transfer to B. So tells you pi transfers to B cross in some cases. And one knows exactly when this happens. So now since B is indefinite, you can associate with this a Shimura curve, which I'll call X sub B. And these constructions that we gave up above, where you take H1 of the modular curve with QL coefficients and then take the pi isotopic component, they can all be repeated in this case. So you can take likewise H1 et al. Of XB QL, and I'll just keep writing pi isotopic component for the same thing. So in this way, you get a Galois action, and you also get a Hodge structure, and so on. So the question is, how are these related as B varies? All right. And the really easy case is the Galois representation, because these Galois representations are irreducible. They're 2-dimensional irreducible representations, and they are determined completely by the trace of Frobenius, the trace of Frob P at all the unramified primes, and we know what those are. And those are the same. They don't really depend on what this B is. So what you get is that if you have two quaternion algebras B1 and B2, then the Galois representations are isomorphic. So H1. These are isomorphic to H1 of XB2 QL pi as Galois, as GQ representations. So this is almost tautological by the definition of functoriality. But you can ask, well, what about the corresponding Hodge structures, the corresponding periods? And in fact, in this case, there are many different ways to relate the periods. But one sort of nice way to say this is one can apply the Tate conjecture, which in this case is a theorem of faultings. So faultings proved the Tate conjecture in the setting, and this will tell you that there's actually a cycle on the product variety that realizes this isomorphism. And then once you have the cycle, then you can, of course, the cycle gives you maps on usual cohomology, and therefore you get the following. You get that H1 of X B1. I'll just write pi isomorphic to H1 of X B2 pi as rational Hodge structures as well. Okay, so in fact, one gets an isomorphism of motives in this case, which is really quite strong. Okay, so just to summarize, the case k equals 2 is particularly simple because you can just work with modular curves and the cohomology of modular curves, and you have this lovely theorem of faultings, which tells you that there is an algebraic cycle that represents functoriality in this case. But the moment you go to the case k bigger than 2, you sort of run into a problem. And the problem is that now you have to look at either hk minus 1 of this variety, which I'll call wk, or you could look at h1 of x with coefficients in the sheaf, which I call lk. And if you have two quaternion algebras B1 and B2, then these varieties are higher dimensional. So for example, if k is equal to 4, then dimension of x B1 so I shouldn't say x B1, but I'll just say w, maybe let me just say this, that so in this case, you're taking the two-fold product of the elliptic curve over y and then taking some compactification. And there's some analogous construction for the case of quaternion algebras. So this variety is three-dimensional, right? So in this case, this is three-dimensional. Let's say wk b1. Was 3. And so really, you would be trying to construct a cycle on this product, and one has no idea how to construct something like this. Okay, so we don't know how to do this. For the Galois representations, you're okay, because again, the Galois representations are two-dimensional, irreducible, and determined completely by the trace of Frobenius. And so we know that Galois representations are isomorphic. But if you want to prove something about rational Hodge structures or an isomorphism of motives, then that's much harder. And the reason is exactly that we don't know the Tate conjecture. In this setting. All right, so that is the case when k is bigger than 2. And finally, there's the case when k is equal to 1. And so by the way, actually, maybe I should just mention a theorem, and I will come back to this in a bit. So there's a theorem which chino, which we proved in joint work with the chino, which is the following. We proved, in fact, that the the Hodge structures, that there is an isomorphism of rational Hodge structures in this case, and moreover, that this is compatible with all the Galois, with isomorphisms of Galois representations. And I'll come back and say something more precise in a bit. And finally, there's the case k equals 1. And in the case k equals 1, it's not even clear what the result should be. In other words, you can do the same thing. You can take these two quaternion algebras B1 and B2, and then you get these two different Shimura curves, XB1 and XB2. And of course, again, the Galois representations are isomorphic, but if you want to relate periods, or there's no notion of a Hodge structure. So the question is really, what should sort of the analog of this theorem be, right? How should one even formulate such a question? So and this is sort of the main point of the talk. All right, maybe I'll stop for a second and see if people have any questions, because it's kind of hard to, without being able to see the audience. Eki, any questions so far?
Okay. Any questions? There's something in the chat, but that was a self-correcting question.
Okay. Yeah, I can't see the chat, or maybe I can, but yeah. Okay, I'm going to ignore the chat. So let me know if something comes up in the chat. All right.
I think there's a question since you asked.
Yes, great. Yeah.
Ask stupid question, but this B1, B2 of weight 1 case is still a Shimura curve.
Yes. Yes.
Okay.
Yeah. Because otherwise it won't transfer. Weight 1 will not transfer to a definite quaternion algebra. At least, right? But they do transfer to Shimura curves.
Okay, thank you.
Yeah.
Kartik, can I ask a
Yes.
question?
Yes, Raghuram. Yeah.
So if you take this cycle coming from Faltings' theorem,
Yes.
and I look at, for higher weight, I look at the interpretation of H1 of X with coefficients in LK.
Yes.
That cycle should give some sort of a map between.
Which is probably 0.
Oh, I see.
Yeah.
I see. That's probably it. Okay, very good.
Yeah. Okay. Shall I go on? All right. Okay. So this is sort of the setting. So the point is that somehow this is an interesting problem, even just in the case of modular forms over Q. And of course, it gets more interesting as you go to other groups. So let me give a few more examples, and then I will explain what we can do. So example 2 is you can take the same thing where instead of starting with Q, you start with F, a totally real field. And again, now you can take the case of higher weight. So you can take forms that, so let's say F Q has degree n. And now your weight is a sort of a set of n integers. And the simplest case is the case when you're in parallel weight 2. And the reason this case is simplest is typically you can find the Galois representations in the H1 of a Shimura curve, but not always. In any case, this is sort of the simplest. But in any case, you can still ask the following problem. You can still formulate the following question. You can start with B1 and B2, two quaternion algebras over F. And you can look at the cohomology of the corresponding Shimura variety and take the pi isotropic components. So I assume, as usual, that I start with some pi, and pi transfers to both B1 and B2, or B1 cross and B2 cross. And you might ask, well, what can we say about these spaces? Are they isomorphic or not, right? So first of all, to have any chance of an isomorphism, you need something about the, you need to know what the dimensions of these spaces are. So it turns out that the dimension of h star of xb pi. So let me first of all, in this case, I'm going to assume that all the ki's are bigger than equals 2 at this point. So you can show that the dimension of h star of xb is 2 to the d, where d is the number of places, the number of infinite places where b is split. Okay. So first of all, if you want there to be such an isomorphism, you'd need that the number of infinite places where these quaternion algebras are split is the same. But actually, you need a bit more than that, because it turns out that the that on the Galois side, the Galois representation depends on the set of places. So not just the number of infinite places, but the set of infinite places where B is split. In fact, is determined by that. So the appropriate assumption in this case is not just that the number of infinite places where they're split is the same, but the set of infinite places where they're split is the same. In other words, what I want to say is that B1 tensor R should be isomorphic to B2 tensor R as F tensor R algebras. Okay. And in this case, one can check that one knows that the Galois representations, so I'll just write it this way. So, and by the way, this is all concentrated in the middle degree. So this is also, I should just say that this is also just HD of XB pi. And the dimension of XB is D in this case. Okay. So in this case, I'll just say that, let's say that D1 equals D2 equals D, then HD x sub B1 pi isomorphic to HD of x sub B2 pi as Galois representations. Okay, and one thing you have to be slightly careful about is that this is not a representation of the Galois group of F. There's a reflex field. Let's call it F reflex. And these are actually representations of the reflex field, the Galois group Q bar over the reflex field. And the reflex field actually depends only upon the set of infinite places where the quaternion algebra is split. And so again, because of our assumption, you get the same reflex field for both XB1 and XB2. Okay, and this is actually this is a theorem due to, I suppose, many people, starting with the work of Langlands. I won't. There are many people that have worked on this: Langlands, Carroll, Taylor, and so forth, and ending finally in work of Nekovar. Recently, Nekovar proved that these Galois representations are semi-simple, and that's sort of recent. Okay, so on the Galois side, you get such an isomorphism. In fact, if you start in this case when weight is parallel, then you should get an elliptic curve, E an elliptic curve over F. And the point is that if you have such a curve, then you can take different embeddings of this of F into C, and each of them will give you some Galois representation. And the Galois representation on this quaternion algebra is the tensor, is roughly speaking, the tensor product of the two-dimensional Galois representations that you get as you run over those places where the quaternion algebra is split, which is why you need to make this assumption that they're split at the same set of infinite places. Okay. But now you can ask the same question about Hodge structures. And you run into the same problem as we had before, which is that unless you're in the case when D is equal to 1, we don't know the Tate conjecture. So again, it's a hard problem to relate the periods of these forms or to relate the rational Hart structures. And I'm going to, I'll state a precise theorem in this case. So maybe what I'm going to do is give myself a little bit of space, which is nice. And I will give a couple more examples and then come back there. Okay, so example 3. So this is just, these are examples where I really don't know how to do anything, but I'd like to advertise them so that you can, people who want to think about it might. So start with the CM elliptic curve. So E, a CM elliptic curve. Say even over Q, but it has CM by some imaginary quadratic field. By some field K. Okay, actually, hold on. Maybe I'm going to, yeah, okay, that's fine. Now to this curve, you can associate a Hecke character, psi, which is of type 1, 0.
Kartik,
Yes.
I have a question.
Yes.
It's Tadashi.
Yeah, hi Tadashi.
Yeah. In the case 2, how about d equals 0 case? Is it easy or difficult?
Well, in the
Probability is just a finite number point.
Yeah, so the question is, what would be the correct question there? It's not clear because there isn't right. There is no Galois representation.
Yeah. Okay.
Yeah.
I see. So we don't consider d equals 0.
Yeah. Right. I mean, I suppose there's something one could say there, but it's not clear to me. Right. It's not clear how you get anything geometric out of that. Right.
Thank you.
Yeah. Thanks, Tadashi. Yeah. Okay. So if you start with the CM elliptic curve, then you can associate to it a Hecke character, which is of type 1, 0. And now you can take the square of this Hecke character, psi squared, which is of type 2, 0. And this has an associated modular form, which is the so-called theta function, theta psi squared. This is a form of weight 3. And so of course, this will be on gamma 1 of n for some n. And you can realize this inside a Kuga-Sato surface. So you can find this in the cohomology of W, where W is, dimension of W is 2. This is some Kuga-Sato surface. This is just by the same construction that we talked about before for associated modular forms. But another place you can find this Galois, so on the one hand, you can find the Galois representation attached to psi squared in H2 of W. But another place you can find this is if you take the self product of this elliptic curve, you can also find it in H2 of E cross E. And so again, it's sort of what you expect then is a cycle on this product E cross W that represents, or that gives you this isomorphism. And I have no idea how to do this. And this is in a way a generalization of this previous question. And the way you should think about this is that this is the form of functoriality here is roughly U1 to U2, or there's some theta lifting in this case. And you can think about this as, so W is fibered over some curve. So this is a sort of universal object. And this likewise is also a universal object. But here the Shimura variety is some finite set of points where let's call it 0. So so it's sort of a generalization where of the previous case, where instead of working just with the ambient Shimura variety, you have to work with some kind of universal object. But the interesting thing about this case is that the base Shimura varieties have different dimensions. And for some reason that I don't understand, this seems to make the problem harder. Okay, and here's another case of something like this, which I'll just call example 4, which is you can start with F, a modular form of, say, weight 4. Then there is this notion of the Saito-Kurokawa lifting of F, which you can think of as a Siegel modular form. So, I mean, to be precise, one gets some packet and so forth, but we can ignore that. In many cases, this contributes to cohomology and contributes to H3 of some Siegel modular surface. So H3 of X, we'll call it H Siegel. On the other hand, the original form F, because it's a modular form of weight 4, also contributes to H3, but now of a Kuga-Sato variety. So the situation now is, again, you want a cycle on W cross X, where this W is now fibered over a modular curve, and X is a Siegel variety. And again, you should have a cycle that represents this. And if you could construct the cycle, then you would get, for example, the rational Hodge structures are isomorphic, and compatibly so with the Galois side and so on. But again, the difference here is really, and I find this case interesting, is because again the dimensions of the base Shimura varieties are different. This is the same thing. Varieties are not equal. And this case is sort of harder to study for that reason. But these are interesting examples to think about if you want to, if you'd like to think about these. All right, so let me get back to this case, because now I'm going to actually state a theorem here, and this is the theorem that we proved with the chino a few years ago, and you can find our paper on the archive. And what we prove here is, so we're in the case when we have K with all the Ki's at least 2. And so of course, there's some local systems, which I'll call L1 and L2. And the local system, so the trivial local system if all the Ki's are exactly 2. So what we proved is the following, that there exists an isomorphism HD X sub B1 L1. Okay, let me do the case K. Actually, it's sort of more, it's painful to write it this. So I'm just going to assume that the K's are all 2 for now. Oh. For simplicity, because so let's just do this case, and the case and K's are bigger than 2 is exactly the same. You have to just introduce some local system. All right, so what we proved is there exists an isomorphism of this sort. So I should just say C. Which I'll call iota, such that, so first, if I take, iota is an isomorphism of rational Hodge structures. So what this means is, if I tensor with C, then both sides acquire Hodge filtration, and the Hodge filtrations match. And secondly, if I tensor with QL, then both sides acquire a Galois action via the comparison with étale cohomology. And then the claim is that I tensor QL is an isomorphism of Galois representations. Okay. So the way to think about this is, previously one knew this sort of thing, that I tensor Q, one knew that the Galois representations were isomorphic, one for each L, one isomorphism for each L, but one didn't know that these isomorphisms were connected in any way. And what we're saying is, in fact, there is an isomorphism at the level of rational Hodge structures that glues together these L-adic these isomorphisms, one for each L. Okay. All right, so this is sort of, so a remark is this is sort of halfway towards proving that there's an absolute Hodge class. That represents functoriality. In this case. So in other words, you can't construct a cycle, but you can construct something that looks like an absolute Hodge class. We still don't know it's absolute Hodge because we don't know what happens for the Durham aspect of the story, for example. But it's still something because it tells you, it's not something that just comes in the trace formula. It's really something quite geometric. So I guess this is a good time to just stop and ask if people have any questions.
Ask some question.
Yes.
In this case, you get a Q isomorphism of this compatibility with Hodge filtration and Galois representations. I think that if you do it over integers, then you get some level raising and lowering kind of primes coming up as the error factors. And especially if this similar variety is not dimension 1, it is kind of conjecturally even hard to predict it. Can you do this kind of thing?
Yeah, so the point is that, right, so not through the methods that we use to prove this. We do have a separate set of conjectures relating periods. For example, Peterson inner products, at least. And we have some very precise conjectures on that. But those, I mean, we seem to have, we use different methods using the theta correspondence. Also theta correspondence, but slightly different methods. But we have another paper on sort of periods, and we can do the Peterson inner products, which is the quadratic periods, basically, but not something like this. Yeah.
Okay. Thank you.
Yeah. Okay. All right. So I'm going to say just very briefly, I'm going to indicate how we prove this because it's going to be relevant to the weight 1 case. So I'll just say sort of idea and the proof. So remember what we want, we have these two varieties, XB1 and XB2. And what we're looking to, what we'd like to do is to construct some cycle on this product, which we don't know how to do. But what we want to do is at least construct the Hodge class associated with this cycle. So we want a Hodge class on something like this. Okay, and the basic idea is that so maybe here's sort of I'll give just some philosophical idea of how how you might think about this. If you look at the Hodge structure, let's just think about the case when the weight is 2, like even when f is q and the weight is 2. Because of course in that case we have faultings, but obviously you would like to give an independent proof independent of faultings if you want to be able to prove this in general. So in this case, the Hodge structure is of type of f is of type 1, 0 plus 0, 1. And so if you look at what's relevant here is you're looking at H2 of this product. I'll just call it X1 cross X2. And the Hodge structure is of type 1, 0 plus 0, 1, tensor 1, 0 plus 0, 1. And so you can see what you get. You get a 2, 0 piece, and then you get 2, 1, 1 pieces. And then you get a 0, 2 piece. So you can see what the difficulty is. The difficulty is somehow that out of these, this sort of 1, 1 part, which is 2-dimensional, one of these classes should be a Hodge class, but the other one should not be. So it's hard to isolate the Hodge class, at least using Hecke operators, because the Hodge class here is mixed up with the other classes. So you can't use Hecke operators on this variety to cut out the Hodge class. So our idea is to sort of embed this inside a bigger variety. So it's a bigger Shimura variety. And construct a Hodge class upstairs and then pull it back. So construct a class upstairs. And then pull back. And the reason why this is good is that you remember we want an H2 class, and that is fixed. It's still H2. So, but if your Shimura variety is bigger, then H2 is going to be further away from the center, the bigger that X is. And it's a basic fact that on Shimura varieties, as you go away from the center, the cohomology becomes more abelian. So it's possible that you might be able to sort of isolate the class that you want using Hecke operators upstairs, and that's exactly what happens. So in practice, you have to replace these by unitary Shimura varieties. So replace these with unitary. Shimura varieties. So and this is easy to do in this case. So there's some unitary groups, UV1 and UV2, and then you take the associated. And now what is X? Well, you take V to be V1 plus V2, and then take the unitary group of V. So in all of this, you have to pick some auxiliary field E, which is a quadratic field, E over F, and F in this case is just Q. So this is some auxiliary imaginary quadratic field. Okay. So by the way, just to recall, all this works in general for general Fs, but I'm just explaining what happens in the case F equals Q and K equals 2. Okay, so what happens is at infinity, this group looks like U11 cross U11 sitting inside U22. And remember that we want to construct a class upstairs. And so what we do here is we use some sort of exceptional isomorphism. U22 or SU22 is almost SO42. And then we use the fact that the class that we want can be constructed by theta lifting from SL2. And this uses what is called Kudla-Milson theory. So in fact, you have to start with a form of weight 3. So there's some auxiliary form of weight 3 that's involved in all of this. So you start with this form of weight 3, and then you take its theta lift. You have to make a theta lift using, because you actually want a form, so you have to put a Schwartz form and not a Schwartz function. And this Schwartz form is the kind of thing that is studied a lot by Kudla-Milson and other people. Okay, and so we construct so we construct some explicit differential form upstairs, and then there's two things that we have to prove. So the first thing is that when we take its restriction, it has the right property, namely that gives you the isomorphism that you want. Okay, and this is some calculation involving periods. And we have to check some non-vanishing of periods. In this case, it's not so hard, but it's really a sticky point to generalize this to other groups. And the second thing that we want to do is to say, all right, this class is actually a Hodge class. So this theta phi g and actually, it's not quite a Hodge class, but we can replace it by a Hodge class. And to prove this, we use the classification of automorphic forms on this group. So it's sort of a big hammer. But this comes from the theory of Arthur and many other people, most recently the work of Kaleta, Minguez, Shin, and White. And to be perfectly honest, it's not completely written out in this case because these forms are non-tempered. However, we do give an independent proof of this classification that we need in our paper, or at least in the latest version. Okay, so where are we? Oh, wow, I only have 10 minutes to go. All right, so finally, let me just get to the weight 1 case. So what happens in the weight 1 case? Right. So in this case, the main problem is it's not clear how to even formulate the correct result. So let's just go back to the case when, let's take the case when f is equal to q. And now we have these two so what happens is that this weight 1 form will contribute to h0 and to h1. And the sort of analogous thing, let's say f is real quadratic, f is, everything works also in the case when f is totally real. So let's just think for simplicity of the case when the when f is real quadratic. So in this case, and again, you can do parallel, either parallel weight 1 or partial weight 1. I'm just going to assume parallel weight 1 because it's a bit simpler. Okay, and now in this case, you'll get contributions to h0, h1, and h2. But the dimensions are 1, 2, and 1. Okay, so the this structure is kind of this is an interesting thing. It looks like you see some sort of exterior algebra here, and this reminds you of what happens might remind you of what happens in the case of locally symmetric spaces. So if there is a case where if you look at not coherent cohomology but even usual cohomology, but you take locally symmetric spaces that are not Hermitian symmetric. Then you do get a similar phenomenon when even usual cohomology is spread out across different degrees. And so there's a lot of work of Ashay and Venkatesh and collaborators, and we have one paper together, which sort of does formulates a conjecture in this case. And the basic point is that if you have a locally symmetric space and a nice a tempered automorphic representation and a tempered cohomological automorphic representation, and you look at the cohomology, it's usually spread out across different degrees. And what we show is the following. We want to sort of give some explanation for how the rational structures in different degrees are related to each other. And the point is that there's some sort of Motivic cohomology, and there's some Motivic cohomology, which I'll call HM, which admits a regulator map to Deligne cohomology. And what we construct is, so this is really Motivic cohomology of the adjoint motive. So to be precise, this is what I'll call it. This is H1M, the adjoint motive. To be very precise, you want to put something like that. And what we show is that the exterior algebra on the Deligne cohomology acts naturally on the Motivic cohomology. So this is one of the main points of the paper. And then the conjecture is that, so of course, so I should be careful and write. But the conjecture is that, so this acts on the cohomology with complex coefficients. And then the conjecture is that if I take the Motivic cohomology, then in fact, this preserves the rational structure. So this suggests that there should be something similar in the weight 1 case for coherent cohomology. And in fact, Venkatesh and Harris have one paper on this where they discuss the case F equals Q, but they do it with mod P coefficients. And more recently, my student Alex Horawa actually studied the Hilbert modular case in great detail. And he, in the Hilbert modular case, so this paper is, by the way, appeared in IMRN this year. So what he does is he, in fact, constructs exactly, he in fact looks exactly at the situation. He looks at what the Motivic cohomology is, and he constructs a map. So again, one has this sort of regulator. And he constructs the action or an action of this of the exterior algebra on the Deligne cohomology on the Motivic cohomology on the coherent cohomology of X with coefficients in omega, where omega is this Hodge bundle and the pi isotopic component of it. So he constructs something like this, and he conjectures that in fact the Motivic cohomology, this guy. So here I have to take the cohomology over C. That's what the Deligne cohomology acts on. And the conjecture is that if I take the Motivic cohomology, that in fact preserves this. And this looks very sort of very abstract, but in fact, you can make this extremely explicit. This is something very, very explicit. So, for example, in the case when in the case when f is real quadratic, then remember you have h0, h1, and h2, and the dimensions are 1, 2, and 1. And there are actually two maps which are called partial complex conjugations. From h0 to h1. And these partial complex conjugations came up earlier in work of Shimura and Harris in thinking about periods, the kind of question that Har asked about, how do you relate periods? And Shimura and Harris have lots of work on this, and they constructed these partial complex conjugations. And so the point is somehow that these partial complex conjugations give you maps from h0 of x omega, xc omega, to h1 xc omega. But these these guys have natural rational structures. And the key point is that the partial complex conjugations don't preserve this natural rational structures, but Horawa's conjecture tells you exactly what linear combinations of these are in fact rational. And these linear combinations will involve logs of some units, because the Motivic cohomology group in this case is some Stork unit group. So for lack of time, I'm just going to refer you to Alex's paper, and he will explain, he writes it out explicitly. So there's some linear combination of, if you start with some class f over here, you get two classes in this way, which I'll call omega 1 and omega 2. And neither of these classes is rational, but some linear combination, something times omega 1 plus something times omega 2 over some regulator is rational. So that's sort of the conjecture. So these, as I said, involve logs of some units, and then this is some 2x2 determinant. Now, this conjecture, I should say, is extremely hard to prove. And it's even very hard to numerically verify this in any cases other than the base change cases, because it's extremely hard. If I give you a class, I mean, it's just hard to write down coherent cohomology classes, and it's even harder to check that they're rational. So it's sort of a hard thing to do. Okay, but in any case, now I can sort of motivate sort of the main theorem, which is, as I said, is work in progress with the chino. So we're in the totally real case. So f is, say, totally real. And my notation is exactly going to be as before. So B1 and B2 will be two quaternion algebras. And now I'll assume these are split at all the infinite places. And so you can take the, and you can whatever is done in the Hilbert modular case, you can do the same thing in these cases. You can sort of make this Motivic action. So you can take h star of xb1 omega and h star of xb2 omega. Yeah, I'll put C. And the theorem is the following, or maybe I should say this, I should not say C over here. So let's say Q. So I'm taking the rational structure. So the theorem is that there is an isomorphism of rational structures such that when I tensor with C, this commutes with all the partial complex conjugations. So in other words, that is the action of the Deligne cohomology in this case. Okay. So I should stop here, and I won't say anything about the proof, but I just want to say that this is sort of the point that in weight 1 you're wondering, well, what should the extra structure be, because we don't have hard structures. But the point is that the extra structure in this case should be the action of this Deligne cohomology of the adjoint motive. And essentially what we can prove is there is an isomorphism of rational structures that is compatible with the action of this Deligne cohomology. All right, and I said I won't say anything about the proof because I'm out of time, but people can ask me about this later on. All right, so let me stop. Yeah.
Thank you. Let's thank the speaker. Any questions?
Hi. So can you please repeat what did you say about the Stark unit? And it's just a previous example.
Oh, I was just saying that this Motivic, in the case when the weight is parallel weight 1, then this Motivic cohomology is some crazy thing in general, but in that particular case, it's some very explicit Stark unit group, some group of Stark units. So you see the adjoint in this case, it's an Artin motive. So it's cut out by some sort of finite extension given by the adjoint. So you take the adjoint of the adjoint representation, and then you have to look at the unit group of L and then look at some particular piece in the unit group. And there's some explicit group of units that you can write down in this case.
Are you like saying like this linear combination divided by regulator would be some kind of log of some Stark unit or something?
Yeah, exactly. So this would be like log of some unit, and this is some 2x2 determinant, where again you have logs inside. Yeah. And you can, Alex writes this out, so you can, I'll make a mistake if I try to recollect exactly what it is, but it's something very precise. Yeah.
Thanks.
Any further questions? So where does the adjoint intervene? Why does the adjoint arise?
So why is it that the adjoint is the right thing? Yeah, right. So that's a tricky question. I mean, okay, in some sense you can if you think about it, if you think about Peterson inner products, right? I mean, this is one thing that you're trying to relate in some way. So here is the point, right? That let me just say this. So let's say that you were interested in just the case when F is Q, right? And in this case, you just have H0 and H1. And you start with you have this partial complex conjugation. It's just complex conjugation. So if you start with a rational class here and then you apply this thing, you don't get a rational class, but you want to measure to what extent is this not rational, okay? And now you can pair H1 with H0, right? Because of Serre duality in this case, and that's rational. So to check if your class is rational or not, or to what extent it's not, you sort of want to pair these classes, but the pairing is exactly the Peterson inner product, and you know the Peterson inner product is related to the adjoint. So that is sort of how that is one way you can see the adjoint coming up.
So a little bit like in Hida's results.
Yeah. All of this is sort of a generalization of Hida's work or relating the adjoint L value to studying the adjoint L value. But if you take it to its natural conclusion, this is where you land, right? The point is, like, you want to really understand how periods on different Schumacher varieties are related, like these quadratic periods, and we know that the adjoint L value exactly comes up when you look at Peterson inner products. And so it's sort of a natural thing. But what happens in this, so in Hida's case, when he's looking at this originally, the adjoint L value at 1 is always critical. But now these are cases where the adjoint L value is not critical. And because it's not critical, you're in the realm of Bailenson conjecture. And so you see these unit groups or these Motivic homology come up. So it's just sort of a natural conclusion of, of all this work relating adjoint L values to periods.
Okay, thanks. You have a huge audience online also. Maybe there's some questions from.
Yeah. Should I see?
Is there any questions from online participants? Okay, maybe not. Any further questions from the in-house audience? Yes.
Can you say something about the main theorem?
Yeah, right. The proof of the main theorem?
Yeah, and also like where does this B1, B2 split at all infinite places come in?
Yeah, well, again, so of course, this is what you should, it's sort of related to the previous thing, right? So let's go back here. So remember that the Gauer representation, the previous, where was this? Right. Yeah, exactly. So it's related to, in the case when K is bigger than equals 2 at every place, we had this theorem before that showed that the Hodge classes were, that you have some isomorphism of rational Hodge structures that's compatible with all the Galois things. And that uses this construction. And of course, there you very much need that the quaternion algebras are split at the same set of infinite places. And likewise here, you need the same thing because again, the dimension of the, but of course here I'm assuming that they're split at all the infinite places because I'm in weight 1, parallel weight 1. If you allowed yourself partial weight 1, then you could also look at quaternion algebras that are only split at some infinite places rather than all. But if you're parallel weight 1, then you have to assume it's split at all the infinite places because otherwise it won't transfer by Jacquet-Langlands, right? So that's why we have to assume that. And the proof, by the way, runs parallel to the proof over here. So one needs to imitate what one does in the previous case. In the previous case, you construct some differential form and then show that you can replace it by a Hodge class. And in this case, so you have some Kudla-Milson theory kind of argument. And essentially what we do is we do the same thing with coherent cohomology instead of usual cohomology. So we construct some analog of Kudla-Milson for coherent cohomology. That's sort of what happens. Yeah. But once again, I mean, this requirement that, I mean, in general, you could work with forms that are, that are partial weight 1, and in that case, you could take quaternion algebras that are not split at all the infinite places, but you still want to make the assumption that they're split the same set of infinite places because even the dimensions of the contribution to cohomology depend on that.
My microphone is dying, so
okay.
Maybe we'll wrap up for the day. So thank you, Kartik. Thank you so much.